Okay, hi there. Our first look at the binary tree world on Ancient Brain. So here's the binary tree world. We click to run it, and it runs like all the worlds on Ancient Brain. If I reload, which I can do here, or I can do via the regular reload or Control or whatever, each time around, as you see, you get a new random binary tree. And it's drawn correctly with all the nodes in relation to each other, whether they're less than or greater than, and we'll look at how it's drawn in the code. And the aim in this, when it runs, is to search the tree for a particular node. So the important thing about this world is that a lot of the action is taking place in the console. As you can see here, it's telling you the console log shows what's going on. So the console, Control-Shift-J on Chrome, might be different on other browsers. You'll find your console. So in the console, we can see what's happening here. If I reload the whole thing, then it's drawn the tree and it's done a search and it's output debug information into the console. Quite a bit of debug information. So we're going to need to look at the source code in order to see what's going on. Okay, so there's a lot of customization that you can do with the console and with your screen, depending on your screen size. I put the console here down the bottom. And now what I'm looking at is what's going on every time I do a run of this world. So when I reload the world, you'll see in the console that it builds the tree, first of all. So it obviously has some random collection of nodes. It has to put them all into a tree structure. It builds the tree, and this is going to show you how it's going up and down to build the tree. And it's going to be your initial job to relate this to the code when we look at the code. So it builds the tree and logs what it's doing in the console, and then it comes down and it's given a search. In this case, it has to search for 6. And this decides how it goes down the tree. And when it doesn't find 6 and it reaches the end and it has to back up, and then eventually it either finds 6 or it doesn't. In this case, not found. So 19, it's searching for in this one. Well, that was easy because it was right at the start. So in our search, the current is 19 and it's found. So the console is logging a lot of information that would be a bit tedious to have up here in the run header. So the next thing to do to get to grips with this world is to look at the code. So we can view the JavaScript code here. This is a world we don't own. I'm logged in here. This world is owned by a different user. I don't own it. When you're logged in, you won't own it. You can view the code. What you can also do then is you can clone it. So I'm going to clone it and then go to my clone page. And now I can edit my clone. So I can edit my clone. And editing is nice because we can make changes and then immediately see the results in the console. And that's really going to help in terms of understanding how this binary tree is working. All right, so there's one thing I just want to look at in this code before we get going. There's a bunch of constants up at the top, which I'm going to ask you to change. Okay, so they're constant for the purposes of the program, but I want you to give the program new constants and see what it does. But the first thing I want to look at is down here. And it's basically 2 libraries that are loaded in order to make all this code work. So there's 2 libraries called node.js and tree.js. And these are loaded up. And once they're loaded, then all the JavaScript for this particular implementation, this particular example of a binary tree gets to work. And actually that JavaScript is quite short, as you can see. The whole program is quite short. But the bit of JavaScript that runs when you load these 2 libraries is pretty short. So I just want to look at where this JavaScript comes from. So we can look over here. We can go back to the original owner. Here's the original owner, Coding Train project. And we look at uploads. And we look at JS. And here you can see there's Node.js and Tree.js. So you can find them that way. Look at Node.js. There it is there. And you have the address of it here. So this is all, at this point, we're still getting used to this Ancient Brain system whereby you can include other people's work in your creations. In this case, you're including these JS files in your program. Okay, and moving on, I just want to point out one other thing. There's a global variable here called tree. So this is outside of all the functions. And tree is basically the data structure that we're looking at. So that means when we do a run, and we've done a run here, in the console, I could just type in tree like that. Just type in tree, there we go. And then I can inspect this variable. This is the data structure. And this actually is the tree. So I'll leave it to you to have a look through this. Left and right, what does it all mean? And there seem to be rights below rights, and lefts below lefts, and rights below lefts. So that's the entire data structure. It's there. I'm not going to explore it for you right now, but just to note, you can just type tree and go have a look at it. All right, and the last thing I want to point out here is that when we actually do the search, it's here tree search X. What was X? Well, X was just a random number. So as we saw, the X may not even be in the tree at all. It's perfectly valid to return not found. So X is some random number, and we do tree search X. But the wonderful thing about the console, and indeed this whole programming environment, is I can just copy that, and I can just type it in here like this, and tree search for 33. And it says search value higher, but nothing to the right-hand side, which is basically means it's not there. Something like that. We can see it's not there. If I search, however, for 18, it's found. So you can do your searches by just typing them in like that. It's a nice programming environment. You can type in the names of variables, you can type in functions and have them executed. It's really nice. Hopefully it'll grow on you. Okay, so that's the introduction to the binary tree world. And after this video, I set you an exercise. In the exercise, I will be asking you to change some of these numbers up at the top and go crazy with these numbers. You can't break anything. All you can do is make the tab run a bit slow, and then you can close it and start again. But you can't break anything on your machine or on the server, so make enormous trees, whatever you like. I also ask you to copy these libraries here, Node and Tree.js. One reason I do that is because in these libraries, they've been edited to add a lot of debug information. You see all this console log stuff, and you may want to comment that out or change it or make it dependent on you setting some option to turn it on or off. So you're to copy everything, make your own version, customize it. There will be instructions in the exercises how to customize it. And you shouldn't find it too hard. It's really at this point we're getting used to the idea of how Ancient Brain works, of how a binary search works, and the exercise is not terribly challenging. And finally, there's one other thing I want you to experiment with, which is this tree is drawn out so we can see how the tree looks when it's doing its search. But in fact, the whole point of doing these searches is really not to draw these trees. You never draw these trees. You only draw them for purposes of debugging. It would be terribly tedious if you had to actually draw tree structures for every state space search you were doing. It's not necessary at all. So we can illustrate this nicely by going into the code and turning off all drawing of anything of the tree. You just get a tree and search it for a node and see how that works. But you don't have to actually have these visualizations. And that visualization might work for 30 nodes or something, but imagine if there's 3 million of them. It's not really going to work, is it? So do a version of this that has 3,000 nodes, and you'll see that visualizations of trees like that don't really work. Having satisfied yourself that, go and change the code so there is no visualization, and then do the tree with 3,000 nodes and do a search in it and realize everything works fine. It's just there's no visualization. So I hope you have fun and hope it all works out.